You're listening to Cool Air Hot Takes.
Welcome to Cool Air Hot Takes. We are back and better than ever for season 2. We're your hosts. I'm Charlie. This ray of sunshine to my right is Dan Gentry. And this show is all about buildings, energy, HVAC. So if any of that is interesting to you, you are in the right place.
Thank you so much to everyone who's listened, reviewed, commented, sent us hot takes and questions. We love the feedback. It's because of you guys that we are back, and we're so excited to jump into the next season. We've got even more industry insights, expert interviews, and of course, hot takes.
Remember, there are a lot of different ways that you can reach out to us. You can send us an email, coolair.hottakes@train.com. You can leave us a review on Apple, leave us a comment on YouTube or Spotify, and also find all of this information in the show notes of every episode.
Now, we've made a few upgrades to the show. We've put in some investment to make sure we're supporting all of our audience. So for our friends in Canada, we're very happy to announce that the podcast is now streaming on all major platforms and available in 575 volt. If you don't understand that joke, find a Canadian and ask him. I love that.
All right, Danny boy, what do we have lined up for today?
Oh, we got a packed episode today. As always, we're going to get you caught up with HVAC headlines. Then we're going to follow that up with an interview with Rob Trickett from Flow Control Industries, and he's going to be talking about PIC, or pressure independent control valves. Going to be a great one. Then we're going to hit the mailbag. We're going to take some listener questions. And then, of course, we're going to wrap it up with the stat of the day.
I love the stat of the day. All right. Our guest today is Rob Trickett. He's the VP of Sales and Marketing at Flow Control Industries. Why is Rob joining us today? Because remember this little ditty, this little hot take? The thing that people should be designing more around ran across another project today that it just needs it, and it's PIC valves.
PIC valves. You're a big PIC valve guy.
I am.
You're a PIC valve guy.
I know. I am a big PIC valve guy, and we're finally doing it here. Pressure independent control valves. I stand by my hot take. More people should be using them and designing with them. So Rob's going to join us today. We're going to walk through all things PIC valve, what they are, how they work, and how they can benefit designs and clients in the long run. But before we do that, Dan, it's good to be back in the studio.
Oh, it's great to be back.
I've got a high expectation of where this hot take is going. But season 2, episode 1, what's the first hot take of the season?
We've had some time off. Maybe our listeners had some time off, let's say, but we're always still working. So my hot take is we need a national week-long holiday so everybody can take a break, shut everything down, and let's just do a nice, long summer vacation holiday. Nobody goes to work, obviously, except for the critical, some people are probably going to have to, but most people.
But let's not you.
Let's take some time off and just enjoy life. We all work so hard. Take your boat out, take a motorcycle out, have some fun, and just don't work.
What do you want to call this national holiday?
Oh, it's the national holiday.
It's called National Holiday.
Yeah, it's huge. It's a week off, and it's got to be in the summer. We all get outside, touch grass, go see your friends. Recharge those batteries. Work-life balance. I'm a big work-life balance guy.
Okay. You got out on the boat last week, didn't you?
For our listeners, my face may appear red. And I've been trying to do good on the sunscreen. But I got some sun.
You did. You did get some sun. Listener, there's a shade of red that we're working with right now.
Yeah, me and aloe vera, we go way back.
Okay.
What do you got?
All right. So I don't actually have a hot take. I have kind of an update, which I think is kind of fun, We had a sponsorship request.
Oh, whoa.
That's right.
Okay.
Pinnacle Marine, president of Pinnacle Marine. His name is Rob McMahon. Big listener, big friend of the show.
Okay.
But we're very happy with our current sponsor. Where, Train does a great job. So thank you, Train.
Thank you.
We got to give Rob a little shout out.
That's a shout out.
Exactly.
That's a shout
So
out.
if you're looking for commercial boats for whatever you use commercial boats for, whether it's a dinner cruise or shuttling people
holiday.
around or a national holiday, reach out to Pinnacle Marine. Thank you, Rob, for being a great listener.
Wow, thank you. That's super cool.
Yeah. All right. Next up, listener, we got your HVAC headlines.
HVAC headlines. Your news today.
All right, listener. It's 6 o'clock in Oslo. Here's your headlines. Headline number 1. A new flow battery takes on the data center energy crisis.
Go on.
This one's from Clean Technica. Let's break down this headline a little bit. So first, they mentioned the data center energy crisis. What is this that they speak of? There's a lot going on with data centers.
Big deal.
They're building out a lot of data center capacity all over the country. And in general, there's not enough power to power all of the data center that they want to build out. And you're seeing this reflective in wholesale energy markets. So if you look at PJM, MISO, they're having all-time high capacity auction prices, which is leading to higher energy demand pricing. And this is a direct correlation to the US primarily not having enough power to feed the data center build-out demand. The second part of it is a new flow battery. Right? And so what is a flow battery? Are you familiar with flow battery?
I have to admit that I have no idea what this is.
All right. It's niche. A flow battery is a form of energy storage. It's similar to the concept of a battery you'd find in your car, only the duration that it provides power is much longer. So you think of typical lithium-ion batteries, like a Tesla power bank, it's going to last for a few hours. Flow batteries are typically designed to discharge over days, if not weeks.
Oh.
Right. So the reason this is attractive to both the data center market as well as utilities is because in general, the renewable energy that we're bringing onto the grid is intermittent. So a lot of wind, a lot of solar. You don't know when it's going to be sunny. You don't know when it's going to be windy. And so trying to plan out how firm that capacity is hard. If you add batteries to it, you firm up that power. And flow batteries are potentially a great way to build out the electricity demand that we need using renewable energy that's coming onto the grid for data centers, for anything that needs electricity. So the next obvious question here is, well, how close are flow batteries? They're actually here. There are pilot projects today using flow batteries. The company that's referenced in this article is called XL Batteries, and they recently announced a partnership with Prometheus Hyperscale Data Centers on a multi-year flow battery agreement. So coming to a hyperscale data center near you is potentially flow batteries. It's kind of cool.
Yeah, that's super cool. I think my takeaway there is it's really cool that data centers are driving a lot of this because they have the need and they have the funds and the capabilities and the scale to actually realistically make it happen.
Absolutely.
And so they drive this early innovation and then demonstrate that it can be done at that scale and then look at scaling up or down or whatever that looks like after there. So good job, data centers.
All right, headline number 2. Shipment data for heat pumps. This is looking at the res space. This article comes from ACHR. Every quarter, AHRI releases numbers on the residential side of heat pump, furnaces, air conditioning units. So first up, gas furnaces. This is that thing that's usually in your basement that's hooked up to all the ductwork that goes around your house. That furnace has a fan in it that also has typically 2 coils. One is a natural gas coil that heats up the air. One is an evaporator coil that cools down the air. So this gas furnace number is the gas component, the heating component that they're looking at. And they are up big year over year, a 22% increase from 680,000 units in 2024 to 830,000 units in 2025. I don't know if that's a rebound number. Mortgage rates have come down, so maybe there's an uptick in home builds there, but I'm not sure what to exactly pin that on. It's probably a number of factors, but it's up big in the first quarter.
I would imagine those to be relatively stable year over year, and that's kind of crazy. It's interesting at a minimum.
All right. So next up is heat pump units, which is that condensing unit that sits outside. It does cooling, but then it can also reverse and do heat pump heating. Those units are up 7.7% in the same time frame. So 880,000 units up to 950,000 units in 2025. My takeaway from that is that there are a lot of people installing hybrid units. Mm-hmm. So they're doing a gas furnace with a heat pump outside. So you get 2 forms of heating. You can do high efficiency heat pump heating when it makes sense. And then when it gets really cold, you go back to gas heating and you kind of get the best of both worlds.
Oh, yeah. And up here, we do hybrid. Obviously, it's a small sample, but I think that's the trend.
Especially in cold climate, because some of the heat pump technology either gets really inefficient where it doesn't make financial sense for the homeowner to do it because natural gas is generally cheaper, or the technology just can't keep up because it gets minus 20 typically here, and you switch over to a natural gas side.
And I think what's super cool is you get a little app with it so you can see what stage you're on. I love, data and apps and like that. It makes me want to get a heat pump and a new control system.
Because you want to use the app.
Yes.
All right. Next up, we've got Rob Trickett, Vice President of Sales and Marketing at Flow Control Industries. We are going to get into PIC valves. Don't go anywhere. Hey there, listener. It's fun talking about massive 100,000-ton chilled water plants. Mr. Big Water Plants over here, Dan Gentry, is always talking about how big these water plants are. But I know most of you are working on smaller plants that have their own set of challenges.
Like getting to higher efficiencies or updating to the newest controls or dealing with tight retrofit constraints for aged equipment.
If this sounds like you, check out the Agility Magnetic Bearing Centrifugal Chiller. Compact size without the compromise.
Oh man, this chiller packs a punch, reducing installation costs and enhancing system performance, and now it's available up to 500 tons.
Ready to upgrade your system? Contact your local Trane account manager today or visit trane.com/agility. All right, listener, episode 1, season 2, first guest. We've got ourselves a real Renaissance man today. Rob Trickett grew up in Michigan. As Dan would like to say, he's a
Michigander.
He spent summers in Alaska commercial fishing. He attended the University of Washington. He did law school in Virginia. He lived in Russia working for a rocket company, which I'd like to explore that one a little bit.
He'll know more about that.
He's an avid traveler with recent trips to Turkey, Thailand, the UAE, Ireland, and Korea. He currently lives in Austin, where he enjoys driving his Rivian, drinking bourbon, hopefully not at the same time, and loves movie quotes. So, of all the gin joints in all the towns in all the world, Rob joins us on Cool Air Hot Takes. Rob Trickett, welcome to Cool Air Hot Takes. How you doing?
I'm doing great. I have no idea how you got all of that information. If you were like somehow planting bugs in my house, but
That was an amazing intro. That is awesome.
I want to hear more about this guy. He sounds awesome.
That was good. Name of the show is Cool Air Hot Takes. We ask all of our guests that come on to bring a hot take with them. It can be in your personal life. It can be in your business life, anything in between. So, Rob, what is your hot take for 2025?
Well, I hope this counts as a hot take, but what I'd say is that all the innovation in the world that happens in the central plant is meaningless unless we get control of the distribution system.
Okay.
I love it. Yep.
And I know that a lot of people are going to be offended by not having anything that they do in the central plant seem like it's meaningful, and that's certainly not where I'm going with this. But I'll give you a couple of examples that go to prove that all the engineering in the world doesn't help if the rest of the system isn't working, right? So on a new construction, there was a project on a large stadium in Las Vegas where they play football that we can't talk about the name of it, but
no idea what you're talking about.
They were actually looking at it as a value engineering project, and I think it was designed for 16-degree delta T, came in leveraging our valves on the distribution side, and of course a lot of other equipment along the way, but we're able to design that at 30-degree delta T, and what that did is it allowed them to remove over $10 million in just structural steel for supporting the piping. So if you just look at the cost that was going into the building construction, it was over $10 million, and not to say anything about the carbon offsets of that. So these things have to work together, and I look at PICVs as an enabling technology, right? It helps everything else to work well. So you've got to have that distribution system dialed in. You can really reduce your load, and that'll help you to have more efficient equipment, but also you can downsize some of that potentially.
So you gave the listener some excitement here, understanding what the outcome can be. But let's start with...
Talk about what does it actually do?
What is a pressure-independent control valve? What problem are we trying to solve with these valves?
So if you look at all of these systems, when you get into commercial HVAC systems, they're using water in a closed loop system. They're moving that water around. And as valves are opening up and closing throughout that system, it's changing the pressure profile at each individual terminal unit, whether that's an air handler or a fan coil. And as those pressures change, as anybody who has ever been in a shower in an older home and somebody has flushed the toilet and it changed the pressure for them, maybe the temperature, right? It makes a difference when things open up and things close. And all we do is we capture any of that change before it gets to the air handler. We absorb any pressure change in the system, and we maintain a constant flow.
And constant flow through the coil equates to a discharge air temperature control that is constant.
Sure. And obviously, if the conditions change, the flow is going to change, but it's not going to change unless the conditions change, right? So maybe another way to look at it is if you had a single lane highway and you had one car that was operating slowly, all of the other traffic would be stuck behind it. In essence, with pressure independent control valves, we're giving every single car its own lane. So it can be as efficient as possible, go as fast as it needs to go, and what it's doing is not affecting the other parts in the system. And that overall calms down the system and allows it to be more efficient, uses less pump energy, and overall is going to use less water.
Well, my big question is, why doesn't everybody use these?
It's a great question. I think in a perfect world, almost every system would be better off. But the reason people haven't gone to them is really twofold. One, this is, I'm going to say, a newer technology, even though we've been around for 35 years. But initially, it was expensive, right? Lots of people had ball valves, standard control valves. And that means that the price was pretty low. We were the only ones for quite a while that were making pressure independent control valves, and the volume wasn't that high, so costs were high. As people moved into it, we started to see prices coming down, and it made a lot more sense, and it is a lot easier to make the argument to move to pressure independent. In fact, it's almost a no-brainer at this point. But where flow control industries came from, our founder actually started in the oil and gas field. He was doing pressure independent control valves for subsea oil applications where he was injecting antifreeze into subsea oil lines that were up to 2 miles subsea. Pressures and temperatures were extreme, up to 10,000 PSID. When he then transitioned and said, hey, this is a great idea that we should use in the commercial HVAC space and the hydronic space, it was really simple to work with 70 pounds of differential pressure. It was
I was going to say, those first ones sound expensive.
Oh man, right? Up to $250,000, right?
Oh,
Set for, 20-year lifespan in a salt environment that is, below freezing temperatures and very high pressures. But making a valve that's going to work in an HVAC system was really easy. And so, we ended up with a valve that really lasts the life of the other equipment that's there, right? And I think where a lot of the other people came from, they were coming up from making simple valves, and this was a little more complex. And there were some issues as those came to market, particularly early on. Some of their parts were plastic. Those were swelling under heating and cooling. Some leaking occurred. And so a lot of people got turned off in the early days on pressure independent control valves. And our job is to go out and get them reinvigorated and to start using them again. But that's why we put in a 10-year warranty with ours. And a lot of that was to address some of the concerns people had.
I want to get back to the advantage side of this, and the big driver on why I'm such a big PIC valve fan is when you can decouple the discharge air control from the pressure in the system, which is what your valves are doing. Instead of lowering the delta T from design, you actually get your design delta T regardless of the load on the coil, which I think is a really, really important point to get across, because most coils will give you full delta T when they're fully loaded. But when you go to part load, which is most of the time, you typically, in a traditional pressure dependent control system, you end up with lower delta T's as you go to part load. And you talk to a lot of people that run plants, and one of their number one problems is low delta T for the entire system. Is the plant was designed for 12 degrees, 14 degrees, and they're at 6, they're at 8. Walk us through what you're solving there.
I'll say two things. First of all, full load, you're absolutely right, should be at design delta T. Mm-hmm. When you back off from that, you should actually be increasing your delta T. Yep. And the reason you can increase your delta T is because you've got all that surface area, you've got all that capacity, and you're only using part of it. And to help illustrate this, any valve can get high delta T. All you have to do is close the valve down and run less water through that coil. Now, it's going to get hot in the room if you're running a chilled water system, right? So that's the key, is that we've got to control the temperature and allow the valve to do what it's doing in the background. It's controlling those fluctuations, and that's what causes the low delta T. So when it's overheating and then coming back down, it's equivalent to, if you were driving a car down the road and you set the cruise control at 60 miles an hour, right? Mm-hmm. That's one system. That's a delta P valve or a PIC valve system. The other system is going from 50 to 70. It's hitting the brakes. It's going back down to 50. Then it's accelerating back to 70. And at the end, it's averaging 60 miles an hour.
Can't stand those people, by the way. I can't stand those people.
Use your
It's so
cruise
annoying.
control.
Oh my gosh.
But one of those systems is going to be far more efficient than the other, right? And that's where you're getting the efficiency, right? It's the braking, if you will, and the acceleration that are causing the inefficiency. And all of that goes back to the central plant then, and the pump energy and the power that's needed to run these systems. And again, if you can do it from the get-go, where, if you're getting a higher delta T, you can actually reduce the size of the pipe because you don't need as much water, right? So now if we reduce the pipe size, that'll allow us to reduce the pump size. That'll reduces the electrical load. And then we can put super high efficient equipment into the central plant, but maybe we don't need as many chillers or we don't need as large of chillers. And so where a lot of people were talking about getting 15 or 20% theoretical more efficiency out of their compressors, out of the different technologies, we can just go and put PICVs out there and see, I've seen 45% increases in efficiency just by changing out the valves. And all we're doing is helping the other equipment to operate more efficiently. It might be a system that has 3 chillers and we're able to let them operate on 2.
So where should people start? What's the general recommendation on where designers should look first to deploy PIC valves?
Yeah, so if we're talking about existing construction, I would look for the air handlers that are closest to the pump that are moving the most water, because those are going to affect overall performance more. It might not make sense to get out to all your fan coil units that are in individual rooms. Let's say it's a hotel and you've got to go in and open up every ceiling. They can't rent the room that night. But if you can get the big ones that are, let's say that hotel is a casino that are servicing the casino floor, those might make a lot more sense. If you're doing new construction, I would argue that anytime you have a coil, whether it's a fan coil, an air handler, you should put in a PIC valve, because by taking out balancing valves, you really don't need to go through and do T and B, certainly not on every single valve. These are coming out pretty well pre-commissioned. It's not going to affect the other valves in the system when you replace one. So there are a lot of places where you're saving money in new construction, and that's to say nothing of the fact that if we can start reducing pipe size and all of those things, even if we just go apples to apples, it's probably a similar or slightly better cost when you take the labor into account.
Yep.
So I would say everywhere that you've got a coil, it makes sense to have a PIC valve.
Is there a rule, like if you can get to 80% of your load on PIC valves, 70%, like what's the general rule of thumb on that?
So when you're talking about a retrofit, what we will typically see is that building will tip into balance somewhere between 60 and 75%, I would say, right?
Okay.
That's helpful.
And you might not get every bit of the savings out of there, but if all you're trying to do is get design delta T, you're going to get that somewhere at that point. But you'll see less than that. We'll see improvements at the individual air handlers, but not enough to make the whole system come into line, if you will.
Right, but the pump energy savings is by the cubed of the flow. So if you can go from a 6-degree delta T to a 10-degree delta T, even if you can't get back to a full, say 12, 15, whatever the design was, that's still a tremendous amount of energy out of the building.
Yeah, and again, we did the Johnson Space Center, and these guys, it's a government building, it's NASA. They didn't have a ton of money, but they knew they had a problem. They were trying to put new buildings on, didn't have the money for a new central plant, so they just came to us and said, hey, how would you attack this, right? We can't afford to go and put PIC valves across our campus. We've got 45 or 47 buildings. And so we took a look and we checked which buildings were operating with the lowest delta Ts that were also close to the plant. And so on the first go round, we attacked 3 of those buildings. They saw the improvements. It was enough to take back to the powers that be to show, hey, look, we improved this. And each year they were doing another 3 or 4 buildings. And then one day, I think everything just worked because that was it. They didn't come back to us. And it wasn't anywhere near that 45. It was probably 30 of the buildings got taken care of.
Sure.
And that's the other side of it, right? We're not just talking about efficiency, but in a campus environment, we're talking about increasing your capacity. So your ability to grow and add new buildings to an existing system, we'll see 15 to 20% capacity improvement pretty commonly.
And how that's super common too in any campus or district energy sort of plant where they have all these chillers that you can't load them up. We need more. And I think it's awesome to think about. You can put in valves and get more capacity out of your system, or design these valves into your system and save $10 million or pick a number. It's like, it's very powerful when we're talking about a valve.
Absolutely. All right. Last one before we let you go here. What's the one thing you want listeners to go away with?
I mean, it comes back to my hot take, right?
All right.
Let's get control of the load out on the distribution side, and then let's attack the problems that are going on in the plant. Because if it's an existing building, we may be able to solve it just by getting that load under control. But even if that doesn't solve everything, it's going to give you the true number that your load is and allow you to properly size everything in the central plant.
Hear,
Amen.
hear.
Yeah.
Love it.
Like it.
All right, Rob. Thanks for coming on today. Appreciate it.
Thank you.
Absolutely. Appreciate your time.
Hey, Charlie, where do you get all your information?
Well, mostly Grandma Diane's 1984 hardcover encyclopedias. Oh, and engineers' newsletters.
Yes, that's what we're talking about. Engineers' newsletters. Listeners, let me introduce you to the ultimate resource for HVAC engineers. Engineers' newsletters offer self-paced learning on topics like acoustics, water piping, ASHRAE standards, and sustainable systems.
You got it. They also have in-depth 60-minute engineers newsletter live videos, which are available on demand. And the best part of all this, it's all free.
Sounds awesome. How do I get in on this?
Just join the over 40,000 professionals who already rely on engineers newsletters. Subscribe now at train.com/en. And now, back to the show.
All right, listener, this one is inspired by you. We're going to hit the mailbag. And as always, send us an email, coolair.hottakes@train.com. Leave us a review on Apple, or leave us a comment on YouTube or Spotify if you'd like us to check out your question and have us kick it around a little bit. First question up to you, Charlie.
So question one, this comes from Pat Vanish in Chicago, Illinois. Question I have relates to site selection for these very large high-tech, i.e. chip fab, etc., and data center projects. It seems like there are some areas of the country that really seek these types of buildings and some states, counties that push back hard on these types of projects. Do you get a sense of how these firms go about deciding where they are going to locate their project? Also, do you get a sense of how different states and counties go about pursuing or pushing away from these firms? It is a great question.
Yeah,
and
Pat, good question.
deciding where to locate, let's say a data center. Power, I think number 1, number 2, and number 3 is available power right now. Other considerations, clustering for higher performance, so locating data centers together or locating them near urban settings, and policy. I can tell you the Midwest is a growing area for data centers because land is cheaper generally, and there's more power available. On the policy side, I think is where you see local pushback. You hear concerns of local groups for data centers around sound, and that's primarily from the HVAC equipment that's outside, from the generators that they have on site, and then pollution from those generators. So running a diesel generator, the construction traffic, these projects can take a long time, brownouts, blackouts from the grid. I think a lot of these concerns can be mitigated or are just trumped up a little bit. So we can design the HVAC systems to limit sound, not a problem. On the pollution side, I don't think that's really there. Generators for data centers, for most every data center, they're only there for emergency backup.
And these developers aim for efficient, clean systems too.
Absolutely. So those generators are only there, they're not there for regular use. And a good case in point on this is what happened in Maryland. So there was a really large data center, and that project almost didn't move forward because they were only granted a fraction of the generator permits they needed for the build out. Yeah. So what happened is the governor signed a new act into law that modified the rule to exempt emergency backup generators for data centers. And now this project is moving forward. Why that is such a big deal and why it's important for communities to care about this is if communities deny a data center from coming in, they're going to go somewhere else. The upside can be tremendous financially. So Loudoun County, Virginia, which is the biggest data center kind of conglomeration in the world, took in $663 million in tax revenue in 2022.
Whoa.
Just from data center operations.
That is wild.
Right. So, Pat, really good question. Thank you for sending it in. And I think we circle back on this and talk to somebody that's actually siting data centers. I think that's a good future episode.
Okay. Question 2 comes to us from Emma Van Fossen in Minneapolis. Thank you, Emma. Her question is, which next-gen low GWP refrigerants count as drop-in refrigerants? Another great question.
It's a bit of a loaded question.
I think, I really would consider very, very few refrigerants truly drop in. Like, take the fluid out, put the other fluid in. Usually at a minimum, you're going to have to deal with oil compatibilities. You'll probably have some controller changes, maybe settings, maybe some sensors. Especially today, there are going to be some differences. Now, when we get into the, say, next-gen low GWP refrigerants, we're talking about a lot of flammable refrigerants. And so when we introduce that into the equation, now we've really taken the concept of drop-in or being able to use existing stuff pretty much off the table, where the designs that are using these slightly flammable fluids have a different design, have different safety aspects that have to be adhered to within that design. So maybe not the answer you're hoping for, but that's what it is.
Yeah, I agree. That concept of drop-in is really, really hard. And I just think the safe, conservative approach, there is no such thing as a drop-in the way that most people think of. I'm just going to swap the refrigerant out and I'm going to get everything that I used to get, performance, capacity, and everything's going to work like it's supposed to.
Yeah, I mean, even when I think about when we changed from 123 to 514, you could take that same piece of equipment, take 123 out, put 514 in, but you're going to sacrifice performance. You're going to sacrifice capacity, lift, temperatures. So you're still going to pay for something.
Yep. All right, listener, that is all we have time for today. We had a bunch of questions that come in. Hang tight for future episodes. We want to get to them. Just did not have enough time. So thank you for sending it in. Please continue to send in your questions. Send emails to coolair.hottakes@trane.com. We will add them to the list. Next up, we've got your stat of the day.
Stat of the day.
Here comes your stat of the day. Stat of the day.
Stat of the day.
All right, listeners, stat of the day. I like this one. I think Dan likes this one because I've been in a car with him and I know which side he falls on. This is fastest drivers by state.
Okay.
Who's got the lead foot?
Who's got the lead foot? And who doesn't?
Who does? Yep. All right, so this came from Mental Floss. Great name. We're looking at average driving speed across the entire state. That includes interstate, highways, urban, all of it. We're going to do top 3, bottom 3. Top 3 in terms of fastest. Wyoming comes in at 71.8 miles per hour, average. New Mexico, 71. And Idaho at 70.5 miles per hour. Those guys are driving fast.
That's fast. You know, I kind of thought Montana was going to be on that list.
I would have totally picked Montana as well.
There. I mean, Wyoming, I get that.
Yeah,
But
it makes sense. All right, bottom 3. You want to take a guess at who the Gordon Lightfoots are?
Gordon Lightfoot. I mean, an eastern state, a smaller state. Let's go with New Hampshire.
Well, who else you got? That you already got. You got one.
I got one. So I wanted to guess New York because I was thinking
That was a
of New
lucky
York
guess,
City.
by the way. Did you say New York?
I wanted to say New York, but then I thought about, well, you got the city there, but then the rest of the state is all big. So then I'm thinking Connecticut or Delaware or something like that.
All right. Well, you did good. Yeah, you're right. The slowest drivers in the country are all in the Northeast. Number 3, Maryland, 54.7 mile per hour average. Vermont, number 2, 52.8.
Okay.
And the slowest, you nailed it. Slowest drivers in the country, New Hampshire, 49.9 miles per hour. They're going slow.
Maybe there's just a lot of beautiful things to see. And
leaf peepers. They're peeping.
Yeah, leaves changing colors. I get it.
All right. Thanks for listening to this episode of Cool Air Hot Takes. We are very happy to be back for season 2. Remember, new episodes are released every 2 weeks on Thursdays. A couple thanks we got to throw out there. First, thank you to Rob Trickett from Flow Control Industries. That was a great interview today. Thank you to the listener for tuning in. And thank you to our lovely wives, Megan and Amber. Thank you so much for the constant encouragement to leave the room and talk about HVAC. It paid off. Look at what we're doing here.
Thank you, ladies. Remember, we're after your hot takes and questions. You can leave us a comment on Spotify or YouTube, leave us a review on Apple, or drop us an email at coolair.hottakes@trane.com. Don't forget, you can also leave us a rating wherever you listen. And until next time, stay cool and keep those takes hot.